about using some of the ideas from yesterday to understand transformers, and then maybe give a little bit of the proof sketches for some things that I talked about yesterday if we have time. So just to recap where we were, I was talking about how memory is a fundamental computation resource. It's crucial in many practical settings. And we were talking about the role of memory in learning and optimization, and if there are trade-offs between the available memory and the information requirement in terms of, say, the number of gradient queries or the number of data points. And we saw this kind of dichotomy in a few different settings that memory. So for example, we talked about convex optimization with first order oracle. I spent about half of my time yesterday talking about this, where we saw that you have access to a gradient oracle, you want to minimize a convex function, and there was this trade-off between how much memory you have and the convergence rate you can achieve, where convergence rate is measured in terms of the number of gradient queries required to find, say, an epsilon optimal point. And then we talked a bit about stochastic optimization, and we'll continue from there. So in stochastic optimization, we were looking at this simple setting where you're just trying to solve a linear system. So you're getting the rows of some matrix A one at a time. And you're also getting the inner product of all of these rows with this unknown vector X, which you're trying to find. And it's happening in the streaming setting where every time step you can get a new data point, and you can go on and can get as many new data points as you want, but you cannot go back to a data point that you saw earlier unless you store it in memory. So you can do a few different algorithms here. You could do something like just Gaussian elimination, which is basically just solving the linear system in D dimensions, store D examples, D squared memory. You can do gradient descent, which will require more examples, but only D memory. And we were trying to understand if there is a trade-off here. And we discussed how this is really an instance of understanding if first and second order methods, not sure if it's this or if it's the internet, because, okay, maybe it's just the internet. Let's see. Okay, maybe I need to stay here. So we saw if that gradient descent is really an instance of a first order method for solving the problem. Gaussian elimination is a second order method. And our goal was to see if there is anything in between. And in general, like, it seems like there might not be. I talked about this, like, that it doesn't seem to be an advantage of having, say, d to the 1.5 memory. So no 1.5th order method in that sense. And improving on the convergence rate of these first order techniques seems to require quadratic memory. So nothing in between the two extremes. And an instance where this gap is large is for ill-conditioned distributions, where first order methods, they suffer from a convergence rate which depends polynomially on the condition number of the problem, which is just the ratio of the largest to the smallest eigenvalue. Whereas second order methods, they can get a much faster convergence rate because the second order methods, they exploit the Hessian or second derivative information, and they can use that to correct for the curvature and make the problem nicely behave. So in general, it seems like we cannot improve on the convergence rate of the second order technique. So there is a class of linear systems with condition number kappa, so that you either require d squared memory or a sample complexity which depends polynomially on kappa. Like this kind of dichotomy that we discussed last time. And today, for most of the talk, and let's see how fast we go, I'll talk about how we can use some of these ideas that I talked about and optimization theory more generally as well to understand how transformers solve linear regression. This is joint work with Deching Fu, Tianqi Chen, and Robin Jia. So I know most of us are from a theory background, so I won't assume too much about transformers here. Mostly we'll be working at a level of abstraction where we won't really need to worry about the details of the architecture. I still hope to make everything self-sufficient, so please stop me, ask questions. It's after lunch, might be a bit tired, so we can make this interactive. And don't hesitate to interrupt me. We can, if there's anything unclear, please let me know, because this might be a little bit different. So our goal here is to understand how transformers solve linear regression. Basically, originates from this phenomena that is observed about transformers and large language models, that they're really good at in-context learning. This is one of the surprising abilities of transformers. It was first pointed out in the GPT-3 paper, and it is one of the powerful things which really enables them to be very, very successful at many applications. So what is in-context learning? So in in-context learning, you're given some examples. Here you have some text in English and the translation of the text in French. You have these three examples. Then you have this new test point, cheese, and the goal is to find out the translation of cheese in French. The difference from usual fine-tuning is that you do not update your model when you see these first few examples. So in usual fine-tuning, what would we do? We would see the first example, we would make a prediction, see what the error is, and then make a gradient update. So basically, we would be changing the weights of the model after seeing every example. In in-context learning, the crucial difference is that we are never changing the weights. So transformers are really good at this. And our goal here is to understand how they do this. And to do this, we'll start with the prototypical setting. And basically, we'll start with like the most basic setting or the fundamental setting that we could think of, which is the same one as we've been talking about earlier. So just the case of linear models. So this setting is literally the same thing as I said earlier. So it should seem familiar. So what we have here is that we have these examples xi, 2 dimensions here. And then we have the inner product yi with each of these xi. There's some unknown vector w star which determines all the labels for the sequence. So if you're seeing all of these pairs x1, y1, x2, y2, x3, y3, we get x4, and then we have to figure out the label for x4, y4. The linear pointer does. Okay, good. I can use that. Great. So transformers are really good at this. So in d dimensions, if you get like d examples, they will already get a very small error. So you want to understand how they do this. And there's a prevailing hypothesis that they do in context learning. So transformers do in context learning by doing gradient descent across layers. So I'll explain what this means in more detail, more formally a little bit later, but let me explain the main high level idea first. So we have this input sequence, x1, xy1 all the way to like this new test point x4. And you can define some objective based on the sequence, maybe the sum of squares error objective. And then you have the sequence and you have these layers of the transformer. These layers are doing something. We don't need to worry so much about what they're doing. The hypothesis, like in a number of influential papers which influenced our work as well, is that each of these layers is implicitly doing gradient descent on this objective. What does that mean? So in the first layer, you start with some initialization of like what this unknown w is. And then you take maybe one or a few gradient descent steps. And then you refine your estimate of the answer, and that gets you to your new estimate, which the second layer receives, and then it maybe refines that, and eventually you converge to something maybe closer to what the true optima is. So the crucial thing here is that because this is in context learning, we are not changing any of these weights. Like the gradient descent is really happening implicitly in the activation. So in the neurons, in the activations, we are implicitly storing some estimate of the answer and refining that across layers. This will be a little bit clearer when I make this more formal, but so that we see where we are going towards. What we'll show is that transformers are actually doing in-context learning by doing something much stronger. They actually seem to be much closer to a second order method versus the first order method. So this should remind you of what we were talking about earlier as well. I'll explain what these plots mean, but if we look at the errors of the layers of the transformer, it seems to resemble a second order method much more closely than a first order method. And I'll go back to these plots later. So in terms of techniques, it's something that you can call like applied theory. So we will be using theory to guide our empirical investigations. So just to talk about the high level philosophy a little bit, because something that I find pretty interesting generally to use as a methodology to understand what is happening with transformers and LLMs. So what do we want to do here? We want to understand how transformers solve a certain problem. You could maybe do that by looking at the behavior of the model, by like looking at the weights and trying to inspect the weights, reverse engineer the weights to figure out what is happening. Because these models are hugely over parameterized, the space of possible solutions can be too large and complex. So it can be pretty hard to reverse engineer things. And this is not even talking about like frontier models. It's even like smaller models trained on toy tasks. It can be really hard to reverse engineer weights. But perhaps we can use some of our understanding of computation and information theory to help refine this search. So this is an image from the Simon's program on statistical computational trade-offs. Basically, the idea is that we do know a lot about algorithms for solving, say, something like linear regression. So just by looking at the input and output behavior of the model, could we say something about what the model must be doing internally? And could we say something about the model cannot be doing internally? So could we maybe rule out entire classes of algorithms just by looking at the behavior of the model without really looking at what is happening in the weights, by using some of our understanding of what different algorithms look like for the problem? So for example, over here for linear regression, we understand the theory really well. So we know information theoretic lower bounds on the best possible rates achievable by any first order method. And remember here, like for linear regression, I really want to understand if these models seem to be closer to a first order or a second order method. So that is a distinction I want to draw. So optimization theory tells us what is the best that you can do with any first order method. It also tells us settings where the gap between first and second order methods is very large. So could we use some of this understanding combined with empirical investigations? I don't think we can just rely on theory. We do have to, at the end of the day, we do have to do experiments to actually see what is happening. But can we have these experiments be guided by theory to help understand what is happening with these models? That'll be the high level philosophy. And what I would want to convince you of are two things: that we can use some of this understanding of statistical and computational trade-offs to understand some of these mechanisms. And two, that the available memory may explain differences in behavior that we see across different architectures. So I'll be talking about some other architectures as well. And claim is that the available memory may explain some of these differences. And I'll try to explain some of these claims and provide evidence for them. Yeah.
Unlike you don't update the weights at all.
So this is in-context learning. In in-context learning, you train the model, and after training, you don't update the weights. Like it's not really about the architecture; it's more like a paradigm of learning.
Like how should I be thinking?
I'll talk about that later. Yeah, I'll talk about it later. Okay, so let me talk about the setup a little bit more formally. So here's the data distribution. So for every sequence of n examples xi, yi, I will draw an underlying linear predictor W star. I'll also draw it from some nice isotropic Gaussian distribution. And for every sequence, I'll also sample a data covariance matrix sigma. For now, just think of the sigma as being identity. So just nice isotropic distributions. And for every I, I'll draw xi from this Gaussian distribution, mean zero, covariance sigma, just identity for now. And the labels will be given by this linear model, where the ground truth predictor is W star. So everything is perfectly fit by a linear model. There is no noise. So that's the data generating distribution. So every sequence I generate this way. And what are some algorithms for doing this? So you could just do ordinary least squares. If you just store x, if x is your matrix of data points, y is a vector of labels, you just do least squares and you use that to find your OLS solution. You could do gradient descent as a sum of square objective, just the gradient descent updates that we talked about earlier. Or you could do something more second order. So this particular second order method we look at is this iterative Newton, but it doesn't matter. You could look at some other second order method too. So this particular method does something like a matrix Taylor series. I won't go into the details because they're not particularly important. But essentially, to do ordinary least squares, you need to find this inverse of this matrix X transpose X. What iterative Newton does is that it iteratively finds an estimate of this inverse. So it's just doing matrix Taylor series. So think of the inverse of 1 over x. You have all of these power series terms. You have all of these higher moments, and you keep adding higher and higher moments, and that gives you a better and better estimate of the inverse of the matrix. So that's what this iterative Newton does. And once you have this estimate of the inverse of the matrix, you plug that into your OLS solution, and that gives you an estimate of W. Okay, so we can talk about the convergence rates of these different techniques. So gradient descent, you need order log 1 over epsilon iterations to find an epsilon accurate solution. This is in the case where all the samples are coming from this nice isotropic well-behaved Gaussian distribution. For iterative Newton, you need more iterations. So you need order log 1 over epsilon. Sorry, you need fewer iterations. You need a lot fewer iterations, exponentially less actually. So you only need order log 1 over epsilon iterations to find an epsilon accurate solution. So the second order methods, they get this quadratic convergence rates, which is exponentially faster. Okay, any questions up to this point?
From attribution, your objective is to figure out whether it's first or second.
Yes, yeah, it's exactly our point.
The memory is, I think, linear.
Yeah, the memory is also, yeah, linear and quadratic. And here we want to train transformers on this problem and see what they do. So we'll randomly initialize a model, like it's this particular model, the GPT, based on the GPT-2 architecture. We'll train on lots of instances of linear regression. So all this model is trained to do is linear regression. So we train on lots of instances of linear regression. So we draw like these sequences, we draw like labeled examples, and then we train on the squared loss. We train the model in order to minimize the squared loss. So the model is given like, see these examples so far. So you have x1 and you have y1, x2, y2, and so on. Then you get xt plus 1, and then you have to make a prediction for yt plus 1, and then you suffer some squared loss. And this is again in context learning. So every time step you have all of the examples so far. This is your context window. You get a new query point, and then you're making a prediction, and then you have some squared loss that you incur. So it's trained, like it's really just trained on linear regression, yeah. So it's not, we are not using a pre-trained model here. It's a few 100 million parameters, yeah, but yeah, much relatively small transformer.
With context learning, if you're not setting the weights, what do we need to train this?
Okay, so when you do in context learning, after training, you're not changing the weights, but at training time, you are updating the weights. So once we train the model, then after that, like you're just given these examples and then you're making a prediction. Okay. And so a transformer, what does it do? It has few layers. So in our architecture, you have these 12 layers. So given this context, and each of these layers, like it processes the input, and then finally you have this final layer, and then your final prediction is given by linear predictor applied on the final layer. So with all of these architectures, at the end of the day, we have a linear model to make a prediction. Same thing with the transformer. At the end of the day, you have a linear model to make a prediction y hat t plus 1 for the next label. Yeah.
When you take some lot of data, this data is not generated from the same distribution or like different distributions.
The same distribution as we'll evaluate it on. Yeah.
And then the ultimate in context learning example again from the same distribution.
Same distribution, yes. So everything is tested in distribution here. So here we want to try to understand what is happening across layers. So we want to probe different layers of this model. And the way to do this is that you can think of the final prediction as this linear probe, this linear predictor applied on the final layer. But you could also train linear predictors on any intermediate layer, for example, the first layer, to try to see what the first. Okay. Wait, oh my god, it's processing all the. Okay, wait. Okay, hopefully it's done with it's. It might, it's not. Yeah. Okay. Oh. I'm not sure what this is doing. Maybe, yeah, maybe I should just not use this. Okay, let me just move here. And yeah. Hey, just remove this, right? We are not sharing this here. Okay. Oh, why did it show up? We were not projecting using that, right?
Yes.
Okay. Yeah. Okay, good. So let me go back. Okay. Okay, good. I think we can resume now. So the final prediction is given by this linear predictor on the final layer. But we can also train these predictors on any intermediate layer. For example, we could train a linear predictor on top of the first layer's activation to figure out the first layer's estimate of the answer. Similarly, we could train a linear predictor on the second layer's activation to figure out that layer's estimate of the answer. So what we're doing here is that you have this model that you train. So this, you freeze the weights now, and then you're training what people call these probes. So these are just linear predictors trained on top of these frozen weights to figure out the best prediction that you can get using that layer's activation. And it's just using a linear predictor. And this is to figure out what any intermediate layer is doing. What is that layer's best prediction of the answer? And by doing this, we get plots like this, which I briefly flashed earlier. So what is happening here? So x-axis here is the number of in-context examples. So we are in 20 dimensions here. We'll have about 20 examples. It's okay if you can't see clearly at the back. And the y-axis is the error on a log scale. These brighter lines denote later layers of the model. And the main thing that you can see here at this point is that the transformer is an iterative, it's doing something iterative. So across layers, later layers, they are getting a smaller error. So it's iteratively refining its estimate of the answer as opposed to looking up the answer or something like that. So something iterative is happening, and our goal is to understand what is the kind of iterative algorithm that is happening in particular. Is it more like a first order technique or a second order technique? And we need a metric to compare different algorithms. You use a very simple metric. Suppose you have an input x1, you have two algorithms which make predictions, say y1a, y1b. You look at the residuals of these two algorithms and look at the residual across a sequence of examples. And then we just look at the cosine similarity of these residuals. So that'll be the similarity of errors of these two algorithms on this particular sequence. Just the cosine similarity between these two vectors of residuals. And the overall similarity between these algorithms will just be the expected cosine similarity over sequences drawn from the data generating distribution. Okay, so now let's go back to our claim from before. Our claim is that transformers match second order rates for linear regression. So here's the evidence for that. So this first plot is just the one I showed earlier, that transformers are improving across layers. So they're doing something iterative. Okay, so now let's go to this one, which claims that transformers are more similar to a second order technique like Newton than to gradient descent. So let me explain what is happening here. Let's start from the one on the left. So this is a heat map. The darker reds denote higher numbers. Each box here, so first the axes, the x-axis is a transformer layer index from 1 through 12. Y-axis is the number of steps of Newton. So we're trying to compare transformers and Newton in this plot on the left. And this is based on the similarity metric that I talked about earlier. And like brighter reds denote higher similarity. So the first thing that you see is that you see this kind of diagonal-like trend. So there seems to be some kind of linear relationship maybe between transformer layers and iterative Newton steps. And it's easier to see if we look at these yellow boxes. So what do these yellow boxes denote? So for say 7 transformers layer, I add a yellow box to like 15 steps. If that 15 steps has the highest similarity with 7 transformer layers based on this metric again that I talked about earlier. And what we see here is this kind of linear relationship again where each transformer layers, at least in this middle region, seems to correspond to 2 or 3 steps of Newton. Okay, so now let's look at the one on the right. So this is transformers on the x-axis and gradient descent steps on the y-axis now. Same thing as before, the heat map denotes similarity. And here now we don't really see this diagonal trend like earlier. Instead, it seems to be like kind of exponential maybe, or at least you seem to need a lot of gradient descent steps to match transformer layers. And the best way to see if this is actually an exponential relationship is to just plot the y-axis here, the gradient descent steps on a log scale. And once we do that on a log scale, we do see a linear relationship. So let's try to make sense of this using some of these convergence rates that I talked about earlier. So if transformers are matching the rates of a second order technique like Newton, So if they get these log 1 over epsilon rates, we know that gradient descent gets an order log 1 over epsilon rate. So we do expect to see this exponential relationship between transformers and gradient descent steps. So that's what we seem to be seeing here. We see this like this linear on a log scale. So we see this exponential relationship. So transformers seem to be exponentially faster than gradient descent and matching the rates of a second order technique like Newton. Yeah, absolutely.
You also think the aspect of the gradient descent.
No, I'm keeping, yeah, everything is in distribution. Yeah. I'll talk about that perspective like in a little bit. Yeah. But now let's just think of it as an algorithm and try to understand what kind of algorithm it is doing. Yeah. Yeah.
Are you saying at the first iteration, the error of the gradient step at the first step closely matches the error of the first layer at the first layer?
Exactly. Yeah, that's what it means. So you could ask now, like I compared with gradient descent, like maybe transformers are doing some other first order technique, which is not gradient descent, but we can rely on our optimization theory here. This is what I was referring to earlier. We have lower bounds which say that like you shouldn't expect first order techniques to be able to do something much better than this, like get log 1 over epsilon like rate. So we don't really expect there to be some other first order technique which is exponentially faster than gradient descent and matches what transformers are doing here. Okay, so let's see if we can use theory a little bit more, like that theoretical understanding a bit more. So let's try to see if we can find a setting where the gap between first and second order methods is much larger so that we can see a bigger difference. And this is this ill condition setting which we were talking about earlier. So on ill condition settings, as we discussed, gradient descent or its variance, they get this polynomial dependence on the condition number. Whereas second order techniques, they can get a much milder polylogarithmic dependence on the condition number. And in general, what we were talking about earlier, we don't really expect there to be something in between. Like at least it seems reasonable to conjecture that we cannot get around these polynomial dependencies on condition number without using a lot more memory. So this suggests a hard distribution as well. So we could sample an ill condition matrix now. So earlier the condition number I was just sampling from a Gaussian with an isotropic covariance, so condition number was 1. So now I'll choose the covariance sigma to have d over 2 eigenvalues at say 100 and d over 2 eigenvalues at 1. And I'll choose the eigenbasis uniformly at random for every sequence. So every sequence has a uniformly random eigenbasis and the covariance matrix has a condition number of 100. So for every sequence of examples, like so x1, y1, x2, y2 up to say x20, y20. So this particular sequence, it has a covariance, data covariance matrix, and I sample that covariance matrix from this distribution. And so earlier every sequence had the same covariance, isotropic covariance. Now every sequence will have a different, potentially different covariance where the eigenvalues all remain the same, but the eigenbasis is sampled uniformly at random. Okay, so what do we see here? So we see that transformers are still able to match Newton on ill condition data. So x-axis again here is the number of in-context examples, y-axis is error, and so okay, if you can't see completely at the back, so transformer layers still seem to be similar to like Newton. So the last layer seems to be similar to 20 or so steps of Newton. So Newton's performance is not affected so much if you go to the ill condition setting as expected, because second order methods, they can correct for conditioning and they can still get a fast rate. So Newton is not affected and transformers don't seem to be affected as much either. In contrast, something like gradient descent gets a lot slower. So even with 1,000 steps roughly, it's still getting a much larger error than what we can get with transformers or with iterative Newton. Yeah.
So how exactly you just take the output and treat that as a prediction?
So at each layer, I have a probe, this linear model that I have trained for that layer, and I apply that linear model on top of the activation of that layer to get a prediction.
This training is separate from all the training.
Yes. So all the training is done, then the weights are frozen, the model is frozen, and then for every layer I train a linear model which tries to do the best it can
based on what this layer has done, based on the activations of that layer.
And power?
sure that this linear layer is not capturing all the complexity of
Good. Yeah, that's a good question. So, for example, if I trained, say, a very complex probe, like I'm calling these probes, if I trained say another deep neural network on top of the activation here, so that could just do the job itself. So the reason here that is why we want to use a simple probe like a linear model. So we know that the final prediction is given by linear model on top of the 12th layer's activation. So that is the same. For that reason, we also want to use just these linear models on top of each of these intermediate layers activation to see what those layers are doing.
Let's say match like higher order networks.
Even if you have more, so layers here are corresponding to the number of steps of the method. So if you add more layers, what we would expect here is that you would be able to match more steps of Newton. Yeah.
If one
Yeah.
like second order methods, can transform to the able to match gradient descent on condition data. So that's some empirical observation we would be noticing.
Right, but what you would see is that if you compare the behavior, like even at 8 layers, if you look at say gradient descent, like say with 800 steps, 800 steps gradient descent on well conditioned data would get much smaller error. 800 steps gradient descent on ill conditioned data, it'll be a lot worse. So transformers don't seem to be affected as much, whereas gradient descent is affected. Yeah.
Question on set actually. We go moving on all 12.
There's an individual probe for every layer, so the different linear model.
The last
one, the trained model is itself the right best probe, right? So during training time, like the last model, like when we trained the model, like at least if you didn't converge to a bad solution, you expect the final linear predictor to be converged to the best possible predictor, the best possible prediction.
With this sort of computational, but this is
Yeah.
not for your new example, right? Like this is not
It's the new examples are coming from the same distribution.
okay.
So yeah.
Concept you're saying that
Yeah. Yeah.
How steps of a gradient descent? Wouldn't it seems like different objects? Wouldn't the better thing to look at would be like as you train the neural network, the final output of the final layer? How goes the rate of that?
So here, like what we want to do is understand what is happening internally, in the sense that if your final layer is giving you a particular error, then how is it arriving at that error? So like I think what you're asking is also a valid question, but like what we are trying to understand here is how are you arriving at that prediction? So like what is happening internally across layers, and what we're claiming here is that internally, like you're doing something second order across layers. So I think in some sense, and these two questions are not that different, because if at the end, if you were only doing something first order, then you would just not be able to get to a small enough error with like a given number of layers, say 12 layers. So you could do something like that as well. But our goal here is to not just understand what is happening at the end, but also what is happening internally, like in between the layers. Yeah, it's a good idea. Okay, and so what we see over here is that in general, transformers seem to still be very similar to Newton, like the same similar heat maps that I showed earlier. Whereas like now gradient descent seems to be even a lot worse, as we expect. Earlier we needed 1,000 or so steps to match transformers. Here we seem to be needing like 3,000 or so. Okay, so we can also ask if you can actually implement a technique like Newton with the given architecture that we have with transformers. And informally, without going into too much detail, we show, like in some sense, what we see in our experiments too, that transformers, you can match k steps of Newton with order k layers and with order d hidden units per layer. So this is saying that you can actually represent an algorithm like Newton. So you could ask, like, can you even like represent something as complex as Newton, which is getting a much faster rate? This shows that you can do that representation. It's not proving that you converge to this solution, but showing that you can represent that solution. So, and this uses, there's been some related work which tries to analyze training dynamics as well, and tries to analyze it beyond linear regression. We can talk about this offline if you want, maybe. And yeah. Yeah, so the first takeaway is that what transformers are doing for linear regression is like something second order rather than first order. So they seem to be getting a pretty fast convergence rate across layer, which explains, like in some sense, their success at in-context learning for linear regression, why they can get to such a small error. So that's in terms of like understanding what transformers are doing here, that's the takeaway. And in terms of like the techniques, what I would say is that we can use some theory, like experiments guided by theory, so theory and experiments together to try to get to this behavior. And that also brings me to this last part of this work. So we can ask what makes transformers suitable for using the second order information. So why are they doing something second order versus doing first order? So that gets to the second takeaway. So to do this, we can compare with a different architecture. Yeah. So doing something faster than like second order. So I think in general with optimization, you don't get like much faster rates than what you get with second order, like at least for the kind of settings that we're talking about here. I think like there's some problems where like these cubic methods and so on get faster rates, but at least for these nice Gaussian linear regression settings, I don't think you can get rates which are faster than this. So there's not really that much more scope beyond second order techniques here. So in order to understand what transformers are, like what makes transformers suitable for using the second order information, let's try to compare with a different architecture, and this will get to the role of memory as we were discussing earlier too. So let's compare with a recurrent architecture, this LSTM. Again, the details are not important. The main distinction is that with an LSTM, you're processing things online. So you're getting the first input, you're making a prediction, but then like this, the first input goes away. You don't get to store it. The second input comes and you get to predict a prediction and so on. In contrast, when you have a transformer, like the only thing that you need to know about the architecture here is that we have this attention which can look at the entire sequence. So you have all of these examples, up to say xt plus 1. You have x1, y1, x2, y2 up to xt, yt. You can look at everything using attention and make a prediction. Whereas with the recurrent architecture, you only see things one at a time. So unless you store something in your state, so store something in memory as you were talking about earlier, you don't get to use that example again. So let's see if that makes a difference. So we do the same thing with LSTMs. We probe the layers. We see what is happening with different layers. And what we see here is that LSTMs actually seem to be much closer to a first order technique like online gradient descent than a second order technique. So this is just the behavior of LSTMs across layers. First, they get a much larger error, which goes to your question earlier as well. Like if you just look at the error, it is much larger than what you got with transformers. It also doesn't seem to improve that much across layers. And this one over here is the x-axis is the number of in-context examples, y-axis is the error. And in general, like LSTMs, this pink line seems to be close to online gradient descent. This orange line over here, transformers get a much smaller error. Like in 20 examples, you're getting like very small error in 20 dimensions. So it seems to be close here. But I think what makes this clearest is to actually see that LSTMs are forgetting previous examples, just like online gradient descent. Let me explain this plot. So x-axis here is timestamp. So what we do over here is that we test the model on a data point that it already saw in the sequence. So we repeat a point that you saw in the sequence. And the x-axis denotes how many time steps ago you saw this particular point. So on the right end over here, you repeat a point that you just saw. So just the previous time step. So timestamp 1, timestamp cap 1. On the left extreme end, you repeat an example that you saw maybe 20 time steps ago. And you see the error of different models here. So what do we see? So online gradient descent, this may be the one that we can understand most easily. So that gets a much larger error if you test it on something that it saw a long time step back. And if it saw something very recently, it gets a small error, which makes sense, right? Like you're doing these iterative updates, there's no reason that you're still accurate on something that you saw 20 time steps ago. You see the same thing with LSTMs. Like they are also getting smaller error on things that they saw recently, larger error on things that they saw before. In contrast, transformers get a very small error if you test them on anything that they have seen in the sequence. And this gets to this ability to have everything be in memory, to have all your examples be in memory. And that seems to give transformers the ability to get a much faster convergence rate. Whereas with something like LSTMs, you seem to be forgetting previous examples, which gets much worse convergence. So so this is like the final takeaway here. So this additional memory that transformers have, the fact that they can see the entire sequence using attention. So really they have quadratic memory, to answer your question from before, because they just have everything available in attention. Like as long as your context fits within your attention window, you have everything available. So versus recurrent architectures, which are processing things one at a time. And this additional memory seems to enable them to learn much more efficient algorithms. And maybe this is an instantiation of this kind of gap that we see in the convergence rates of different algorithms with different memory. Any questions about this? Yeah.
So if I didn't know, I'm considering that there are some OGD versus defense method. Like if I
So what the
read the following curves for
OGD versus yeah. Yeah, so Newton's method as well. So if you like, this is Newton's method with a very small number of steps, with 5 steps. So with Newton's method with 5 steps, it just gets a flat. So the error is not 0 because you're only doing 5 steps, but it's flat across all the sequence because if you use Newton's method as well, you're really doing something on all of the examples together versus doing something one at a time. So it's flat, and I guess the reason that we have this is because I also compared, if you look at just the error, the Newton and LSTM seem to be similar in terms of the error. So this, like, the reason that we did that comparison is to see how even 5 steps of Newton, which doesn't get a very large error, the error is similar to what you get with OGD, but it is very different in terms of the type of error. Like it's not forgetting previous examples versus with OGD or LSTMs, you're forgetting previous examples.
So if I look at this figure,
yeah.
Like, was there any way to guess that OGD would forget and that's?
I think, yeah, that would come from, like, for this nice distribution, you could just analyze it. I think if your data is coming from a Gaussian, then I think you could probably just analytically compute what the error should be on something that you saw 20 time steps ago, or at least like simulated, obviously. But I think it's basically like with OGD, you're doing corrections one at a time. And there's no reason, like the thing that you just saw, like with the right step size, you can be perfect on that. But there's no reason that you'll be perfect on something that you saw. If you haven't converged yet, you won't be perfect on something that you saw a long time step back.
Make sure it's not overfitting the data is and completely so that
yeah, even if you do that, like you could do regularization to make sure that you're not changing so much, but you would still not be able to get a small error on something unless you have converged. You could increase that window, but unless you've actually converged, once you converge, you're done because then you're getting small error on everything. But till you have not converged, you wouldn't be able to like get. Yeah, exactly. Yeah, I was like, there was this last part that I was thinking of talking about, but we can talk about it offline. So if I want to talk about it in 30 seconds, basically we try to understand memory lower bounds for detecting certain planted problems, things like in the streaming model. So things like planted clique and sparse PCA, and this is based on some recent work. We can talk about this offline. I think I'll just stop now. I think I'm already a little bit over time. You can take any questions or switch.
All right.
Yeah.
So it's a combined question. So you did on a quadratic problem with converge in one step. So you're doing iterative Newton.
Yes.
Why you're getting this poly.
That's true.
Poly log, gamma.
That's true. Yeah, if you're actually doing full Newton, you would converge in one step.
Good. So now the reason I say this is like the deeper question is why iterative Newton? Like,
Yeah.
I chosen.
You could have chosen, yeah. So what we did do, we compared with some other second order techniques like VFGS, and like those also get a similar convergence rate. So I don't think the transformers are doing iterative Newton. What I think they're doing is something within the class of second order techniques. And we did compare with some other second order techniques which get a similar convergence rate, and you see similar results. So I don't think it's the case that they are doing Newton. It's more about the class of algorithm that we can say something about.
You're saying transformers can converge super linearly across layers, but
yes,
they could be implementing anything that converges.
They could be implementing any of these algorithms that do that. Yeah, that's exactly right.
It's like the common theorem where you said that
yeah,
transformer
where
a transformer could implement a
Yeah.
Definitions are
Yes.
K plus 8 layers.
K plus 8.
Plus 8.
Yeah. So yeah, I think it's probably an artifact. But what we do see is that like you need some initial layers in order to set things up to do your iterative Newton update. And we do see a little bit of that in our results. I don't know if that's just a coincidence. It could just be. But you see like that initial few transformer layers, they're not doing as much. It's a little bit flat in the beginning. And in our construction as well, like before doing the iterative Newton, you have to like basically set things up so that you have matrices in the right way. After that, you can do one set of Newton with one layer. So I don't. It could be a coincidence or it could be related to that.
Right.
Yeah, it's probably just priming. Yeah.
All right. So let's thank Vatsal again.
Thank you so much. Yeah. Thank you. Thank you so much. Oh, I am. That's true.